Okay, so in this video, we'll talk about what are galvanic cells or voltaic cells. So a galvanic cell or a voltaic cell is essentially a cell where a spontaneous redox reaction occurs to generate electrical energy. So this is a cell that produces electrical energy. This is where a spontaneous redox reaction occurs. A spontaneous reaction, as of now, you guys understand that delta G for spontaneous reaction is always less than 0. Later on in this chapter, you will see how we can figure out if a reaction is spontaneous or not based on the potential difference as well. But for now, just remember that a galvanic cell or a voltaic cell, which is a cell where a redox reaction, which is spontaneous, is happening and it produces electrical energy. And there's an opposite cell than that, which is called as a, okay, let's talk about that later on. There's also somewhere where we can have a non-spontaneous reaction where we actually give electrical energy or power to our redox reaction, a non-spontaneous redox reaction. We'll talk about that later on. That's called an electrolytic cell, but we'll talk about that later on. For now, let's focus on galvanic cell and voltaic cell. So it's going to be a lot of discussion. All the theory that I discuss is listed in the PowerPoints, but I'm just going to show you the image of a galvanic cell or a voltaic cell and then give you all the description about it. Okay, but all the stuff that I'm talking is also listed in your PowerPoint. So all those details you'll see in your PowerPoint. So this is essentially how a galvanic cell or a voltaic cell looks like. This is the picture of one of a galvanic cell. Okay, what do you see right here? These two. A galvanic cell will always consist of two components. Actually, it has three main components. Okay, one of those components is a electrode. Okay, so a galvanic cell will always consist of two electrodes. Let me write it here. Okay, it always consists of two electrodes. One of them is an anode. The other one is called the cathode. Okay, one of them is anode, one of them is cathode. This right here that you see is our anode, a zinc anode. The second one that you see right here says cathode. This is our copper cathode. Don't worry about zinc and copper as of now. Just remember it always consists of two electrodes. One of them is anode, the other one is cathode. The anode is where always oxidation occurs. This is where oxidation occurs. A cathode is where always reduction occurs. How can you remember this? Anode and oxidation, they both start with a vowel, and cathode and reduction, they always start with a consonant. Okay, so anode is where oxidation occurs, cathode is where reduction occurs. This is what you should remember. Okay. Next, what happens in a voltaic cell? As I said, it always has spontaneous reaction occurring in here, which produces electrical energy. So if I connect a galvanic cell with a bulb, because of the spontaneous electrochemical reaction that is happening in here, you would see this bulb light up. Okay, because it produces electrical energy. Okay, moving on, this galvanic cell always consists of two half reaction. Like every electrochemical reaction, there are two half reactions that are happening here. One of them is oxidation, one of them is reduction. So these two cells that you see are called the two half cells. So each half reaction is happening in one half cell. So this is wherever the anode is our oxidation half cell, wherever the cathode is our reduction half cell. Now what do these each half cell consist of? Like you see in the image, each half cell will consist of one electrode and an electrolyte. So this is our electrode, which is anode, and this solution right here that you see is our electrolyte. So these two solutions that you see are electrolytes. So each half cell consists of electrode and an electrolyte. And the next important thing that you see in galvanic cell is the salt bridge. So in order to complete the circuit, so what you see right here, this is electrolyte, this is anode, which is connected by a wire to the cathode, which is also immersed in its own electrolyte solution. But the electrical circuit is not complete yet unless you have this salt bridge connecting it. So this right here, what you see in the middle, is the third component, which is very important, which is called the salt bridge. So electrolyte solution, electrodes, and the salt bridge. Those are the three important components. What is the purpose of salt bridge? Salt bridge essentially completes the electrical circuit. It usually consists of ions that do not participate in the reaction. So in this galvanic cell, the reaction that is happening is zinc is getting converted to zinc 2 plus, and copper is being produced. Copper 2 plus is getting converted to copper. Okay, don't worry about that as of now, but this is the reaction that is happening here between zinc and copper. So the salt bridge usually consists of ions that do not participate in reaction. Most of the times those are potassium ions or chloride ions present in something like a gel. This allows for the circuit to be completed so that once electrons are being transported across the electrodes, the ions can be transported across the salt bridge. Okay. Now what happens during a reaction? Like I said, anode is where the oxidation occurs. So what is oxidation? Oxidation is loss of electrons. So electrons will be lost in this step. Right here, anode will lose the electrons. What does cathode do? Cathode is reduction. So this is GER, which is gain of electrons. So this gains the electrons. So anode loses electrons, cathode gains the electrons. So that's why in a galvanic cell, you will always see that electrons are being transported from anode to cathode, because electrons are being lost from this step right here at the anode, and they're going towards the cathode because cathode is gaining those electrons. Okay, so anode is always the source of electrons, and cathode is always where the electrons are being used up. So electrons are used up at the cathode. So that's the difference between these two electrodes and what happens at the two electrodes. Okay, so always electrons you're going to see are going in this direction. Perfect. So now the next step that I want to explain, let's say if we are working with an actual reaction. So this is the net reaction that we are working with. Okay, like I said, zinc is reacting, zinc which is solid is reacting with copper ions to produce zinc 2 plus and copper solid. So let's first divide this reaction into two half reactions. So zinc right here, you guys know by now how to divide the two reactions. So let's write our two oxidation and reduction reaction. Zinc is changing into zinc 2 plus, copper 2 plus is changing into copper. So we'll write it into two reactions, which is zinc is changing to zinc 2 plus. Right, let's balance this reaction now. So first step is balance everything other than oxygen and hydrogen. There's no oxygen, hydrogen, so we balance zinc. Oxygen, no, not present. Next step was hydrogen, not present. So what do we balance? Charge. How do we balance charge? By adding electrons. How many? What is the total charge on the left side? 0. Total charge on this side? +2. So we have to make the charge equal to the lesser total less charge, which is we can make the charge equal to 0 by adding 2 electrons on this side. Okay, so that makes your one half of the reaction as zinc changes to zinc 2 plus 2 electrons, right? That's how we balance it. Now let's balance the second half, which is copper 2 plus is changing to copper. So same step, copper 2 plus is changing to copper. Balance every element other than oxygen, hydrogen. Balanced. Do we have any oxygen to balance? No. Do we have any hydrogen to balance? No. What can we balance next? Charge. Charge on this side is +2. Charge on the other side is 0. So again, we have to make the charge equal to this lesser charge, which is 0. And we can do that by adding 2 electrons on the reactant side here. So that gives you this, which is listed right here. Okay. Now, in this step, what is happening? This is electrons are being lost. So this is loss of electrons. So this is oxidation. That's why it's listed right here where anode is. What is this side of the reaction? Copper is gaining electrons. Copper 2 plus is gaining electrons. So this is Gain of electrons is GER, so reduction. That's why it's listed on the side of the cathode. Okay, so that's how you can identify what reaction is happening at the anode and what is happening at cathode. Now, why is it important to see these reactions? What would happen eventually? This anode that you see right here is zinc metal. This cathode that you see right here is the copper metal, right? Because ions are present in ionic form. You cannot have ions as solids. And what do you need for electrodes? You always need a solid to make an electrode, right? So these ions cannot make electrodes. Ions are always aqueous. So this electrode will always be made with whatever solid metal you see. So this is zinc, this is copper. Now what would happen at the anode? If you think about, if I let this reaction go, what is happening? Zinc is getting converted to zinc, producing electrons. The electrons are getting transported to cathode, and the copper ion in this step is taking up these electrons and is converting it into copper, right? So if you think about this, eventually what will happen? The zinc, where is this zinc solid coming from? This zinc solid is right here. And what is the zinc 2 plus ion? They are right here in the electrolyte solution. So what would happen eventually? Over time, if I let this go, zinc anode will lose more and more zinc ions, right? This zinc metal is losing the zinc ions, and those zinc ions are getting converted into aqueous solution. So this anode is going to eventually lose some of the mass over time. Whereas the cathode on this case, what is happening to copper? Copper ions from this solution are taking up 2 electrons and are changing into copper. And what would happen? That copper will eventually get deposited right here. So if you see this reaction happening in front of you, what would happen? Over time, this zinc, the mass of this zinc is going to reduce. So it will slowly become smaller and smaller in size, or thinner in size, whereas the copper cathode is going to increase in size. Why? Because more and more copper will keep on depositing on this copper, as copper 2 ions here are getting converted into copper, and those copper will deposit on the cathode. So mass of the anode reduces and mass of the cathode in this case will increase. Okay, all right. And like I said, salt bridge does not participate. Whatever is present here does not participate. It only allows these ions to be transported across if needed. So it only makes sure that the ions or the electrolyte solutions are balanced across. Okay, the solutions are neutral, the charges are neutral. Okay, and one more thing that I want to mention here, that usually whenever you would see a galvanic cell written out, always it's just a formal way. Why is it? Don't ask me why. It's just that this is the formal way. Whoever came up with this cell, this is how it's written out. Okay, anode is always written out on the left side, cathode is always written on the right side. So whenever you draw a galvanic cell, it would always consist of anode on the left, cathode on the right. That's how it's just written out. Okay, there's the reason behind this is just that this is a rule. That's how it's done. Usually, most of the times, that's a rule. Sometimes people don't follow the rule, but that is how it should be done. So anode on the left, cathode on the right. So that's everything about a galvanic cell or a voltaic cell that you need to know. And again, all of this is also listed in the PowerPoint. So you can see right here, it explains what half cell is, what's present in half cell. It explains how it works. So what happens at the cathode, what happens at the anode. And like I was showing you, eventually once this reaction is completed, what would happen? You see right here, this was the zinc metal. We started with a whole mass. Eventually you would see after several hours the zinc anode weighs less, as zinc is oxidized into zinc ions, and ions become aqueous, so they go out from here into the solution. What happens to copper? More and more copper is deposited, so the copper cathode gains mass over time as copper ions, which were in the solution, get converted into copper and they get deposited on the cathode. So after a few hours, that's how your electrodes would look like. Okay, now moving on, this I explained to you already. Anode is the one that produces the electrons, right? And cathode is the one that takes up the electrons. So one thing that I missed here is that charges of the electrodes, the anode would always have a negative charge. So the negatively charged electrode is anode. Okay, the positively charged electrode is called the cathode. Why? Because it's going to accept electrons. So remember, the electrons are always going in this direction, right? And left is always anode, right is always cathode. So if electrons are going in this direction, you can assume it's not really true, but if you want to remember it, how can you remember it? If this is my electrolyte solution, right, and these are my electrodes, anode is always negatively charged, cathode is always positively charged. Electrons are going from the negative to the positive, right? They don't like the negatively charged anode, so they go away from negative towards positive. So that's how you can remember it. But remember, anode is always negative. Anode is where oxidation occurs. Cathode is always positive. Cathode is where reduction occurs. Okay, and electrons are always going from anode to cathode. So those are the things that you should remember. These, how can I ask you this, Justin? Like normal multiple choice questions. Okay, what is the negatively charged electrode called? Anode. Or what happens at the anode? Is it oxidation? Is it reduction? Is it oxidation reduction? Is it none of the above? So you should know that it's oxidation. Okay, those are the simplest questions that you can get. Lastly, we also discussed the salt bridge. So what is the purpose of salt bridge? It completes the electrical circuit and allows the ions to flow through both half cells. It essentially maintains the electrical neutrality by allowing excess zinc ions to enter from the anode and excess negative ions to enter from cathode. So it essentially maintains the electrolyte solutions at neutral charges. Okay. Now this is showing you the flow of the charge in voltaic cell, which I already explained. How are the electrons going? If this is my oxidation half, reduction half, electrons are going from oxidation half to reduction half. They are going from anode to cathode. So whatever wire connects the anode and cathode, that's where the electrons are flowing in this direction. Okay. And it shows right here as well. By convention, a voltaic cell is shown with anode on the left and cathode on the right. Now, how can you write this reaction? Every time if I ask you, can you write a voltaic cell expression? You cannot draw me the voltaic cell each time, right? So we usually use this notation to write a voltaic cell. So remember, the notation of a voltaic cell consists of this. Now, where did I get these from? This bar, in the first single bars that you see, those are just the bars showing you reactant and product, separating the reactant at the anode, product at the cathode. Product at the anode. Reactant at the cathode, product at the cathode. So again, anode is written on the left, cathode is written on the right. What separates the cathode and anode? The salt bridge. How do you show the salt bridge? By drawing double lines. So double lines means these are my two half cells. Okay, double line separates the two half cells, and this is also showing you what a salt bridge is. So double line shows that the half cells are physically separated, and this is showing you what the salt bridge is. Okay, this is right here, salt bridge. Salt bridge separates two different electrodes. The electrode is anode on the left. What is the reaction that's happening at anode? Zinc solid is getting converted to zinc 2 plus. So only thing that you write here is your reactant and product, and you omit the electrons. Okay, what happens at the cathode? At cathode, copper 2 plus was getting converted into copper solid. So that's what we wrote right here. And how do you separate the reactant and product? With a single line. So a single line shows a phase boundary between the components of a half cell. Phase boundary mean why? Because the phases are changing. Solid is changing to aqueous. Here aqueous is changing to solid. So it's also called a phase boundary, but essentially what you're separating is the reactant from the product. Okay, so always write your reactant first, product afterwards, reactant first, product afterwards. Okay, so this is notation of a voltaic cell. Usually you don't include concentrations here, but if we want, we can always include concentrations here as well. So if I want to include concentrations, you can write the concentrations right here. Now remember, solids don't have a concentration, which we have discussed before as well. Concentration is always of an ion because they are present in aqueous form. So only aqueous solution have concentration. So you can write the concentration of aqueous solutions in next to them in parentheses. But most of the times, if it's not written like this, it just means that it's 1 molar. You can assume that. Okay, so that is a scientific notation for a voltaic cell. It tells you what are the two half reactions that are happening, and which reaction is happening at anode, which reaction is happening at cathode. Anode is left, cathode is right. Okay. Right. The next thing I want to explain is, we talked about electrodes right now, right? The electrodes are usually made up of solid, remember? So in our previous example, we had zinc and copper. Now, what if our reaction does not have a solid? Our reaction is such that both the reactant and products are aqueous. There is no solid present. What would we do in that case? In that case, we use something which is called as the inactive electrode. Okay? There is something that's called an active electrode and an inactive electrode. An active electrode is the one that actively participates in our reaction. For instance, in our case, zinc, the first example we saw, zinc solid was getting converted into zinc aqueous. This was our reaction happening, right? Zinc 2 plus ion plus 2 electron. This was our reaction. Our electrode was made up of zinc and it was participating in our chemical redox reaction. Okay, which means this is an active electrode. Okay, so either it can be product or it can be reactant, doesn't matter, but it should be participating in the reaction. If it is, it's called an active electrode. If it is not participating, it's called an inactive electrode, but it's only present there as a surface. Okay, it only helps you to complete the circuit. It just provides a surface for the reaction and completes the circuit. It does not participate actively in the overall reaction. So why is it important? These inactive electrodes are necessary when none of the reaction components can be used as electrode. And I'll show you an example right now. Some examples that can be used are graphite or platinum. So we can use a graphite electrode or a platinum electrode as inactive electrode because usually they are unreactive. They don't participate in your reaction. So they can be used as inactive electrodes. So let's look at an example of a reaction where we would need an inactive electrode. So for instance, right here, if we are doing this is overall reaction of the cell. Okay, so this is the galvanic cell. This is the overall reaction that is happening. So what is happening in this case? We will identify the two reactants and two products first. So what's happening? MnO4 minus is getting converted to Mn2 plus, right? And I minus is getting converted to I2 solid. So what is the oxidation reaction? Oxidation is I minus is getting converted to I2 solid. So I2 solid is our product. In this case, product mean it will be produced. So if I cannot have an anode with a product, I can have I2 solid here if I want to, right? Because there's one solid component here. What about the reduction reaction? The reduction reaction is where MnO4 minus is getting converted to Mn2 plus, right? So this is also ion. My reactant is ion, which is aqueous. My product is also ion, which is also aqueous. So I don't have any solid components here that I can use as an electrode at the cathode. I need to use something as a solid to make an electrode, right? So what would happen in this case? In this case, we would use inactive electrodes because we don't have anything solid here to use. So inactive electrode here will just act as a surface. So in this case, you can see both of these cases, we are using carbon electrodes. So C stands for carbon. Carbon is essentially graphite, right? I hope you guys know that already. Graphite is essentially another form of carbon. So we're using graphite electrodes here because it doesn't participate in reaction. You can see right here, this reaction is no carbon whatsoever, right? So what would happen here? I minus will change to I2 solid. So I2 will start depositing over time, like it's shown here. And in this case, the reaction, whatever reaction is happening, it's going to happen in the solution. So MnO4 minus would be present in solution, Mn2 plus would be present in solution. Only thing this carbon would do, it would help us in completing the circuit by transporting the electrons. So electrons again would go from negatively charged anode to positively charged cathode, and those electrons would be used up by MnO4 minus to convert into Mn2 plus, right? And if I ask you, can you write what is the notation for a voltaic cell in this case? In this case, the first reactant would be what's again left would anode, right is cathode. So what's happening at anode? I minus aqueous, don't forget the phases, is getting converted. So my single line in between Forget about this line that I just drew. This single line in between is getting converted into I2, which is solid, separated by salt bridge. What's happening at cathode? At cathode, MnO4 minus, which is also aqueous, separated by a single line, gives me product which is Mn2 plus aqueous, right? That explains you this is the reaction. Now, since our anode and cathode electrodes are different, you have to write the name of the electrodes as well. So in this case, the electrode is graphite, so you'll write graphite in the front. Same thing at the end, you have to write my cathode is also graphite, so graphite at the end. The clearer depiction is right here. Okay, so you do have to write down whatever is your component, whatever is your anode and cathode. If it's different from your components, you write down their name and put a single dash between your reactants and products and your cathode and anode as well. Okay, so that is a galvanic cell. Now let's talk about why is this galvanic cell important and what are we talking about cell potential. Okay, now let's talk about how these galvanic cells are related to cell potential. I just mentioned this term cell potential initially. So today in here we'll talk about what exactly is that cell potential that we were talking about. Okay, so you saw in a galvanic cell what happens. This is showing you an example of galvanic cell. When a spontaneous reaction is happening, it produces energy. How does it produce this energy? Okay, how does it produce this electrical energy? For a spontaneous reaction, what do we know as of now? We know that delta G for a spontaneous reaction is a negative value, right? Similarly, remember that E, or the cell potential, E cell for a spontaneous reaction is always a positive value. I'll explain you what is E cell, but remember this, they always carry opposite signs. These are both for spontaneous reaction. For a spontaneous reaction, delta G is negative, but E cell is positive. Now what is E cell? E cell is cell potential that is created in a galvanic cell. So when a reaction is happening in a galvanic cell, what happens? The electrons are being transferred from the anode to the cathode, right? That creates a potential difference, electrical potential difference between the two electrodes, and that potential difference, again, this is difference in energy, right? So energy, this energy difference is called as the cell potential, electromotive force, or cell voltage. So this cell potential is essentially the electricity that is produced. Okay, what is electricity? Electricity is electrons, right? When electrons are moving, it produces electrical energy or electricity. It produces a voltage difference or a potential difference, and that difference is referred to as cell voltage, EMF, or electromotive force, or cell potential. That's exactly what this E cell you see right here is. Okay, so this E cell for a spontaneous reaction should always be equal or greater than 0. It should always be a positive number. Okay, so now whenever there is a galvanic cell, remember there are two halves that are happening. So one half is the cathode half and the other half is the anode half. So whatever happens at the cathode, that is one half cell. This half cell has its own potential, so its own E value or E naught value. This cathode right here is the other half, so it has its own potential value or its own energy, electrical energy, right? E naught value, E naught potential. These two, when you connect them together, that creates a potential difference, and that potential difference gives you E cell. Okay, so that is the difference between E naught of a cathode and E naught of a anode. All right, so each half cell has its own potential, and then that combined together gives you E of the cell. All right, So each half cell has its own potential, remember, and combined together it gives you E cell. Now try and understand that from here. Those E naught half cells are called the standard potential. Specifically, we have standard reduction potential. Now, this is where it kind of gets confusing. What is standard reduction potential? Standard reduction potential is the voltage associated with a reduction reaction at an electrode when all the solutes are 1 molar and all the gases are 1 atmosphere. E naught equal preference to be reduced. So E naught is a reduction potential. Remember that. Now we are not talking about what's happening at cathode and what's happening at anode. Okay, we are only talking about reduction potential. So whatever is happening is getting reduced in this case. Okay, there's no oxidation happening here. When we're talking about standard reduction potential, we're only talking about potential of a reaction which is reduction reaction. Okay, so this is just a standard way of writing the reaction potential so that people don't get confused. The standard reduction potential is the normal form of a reduction potential that is written out, which means when this reduction reaction happens at an electrode such that at 1 atmospheric pressure and the solute concentration is 1 molar, this potential would be equal to E naught value. And those E naught values are standard for a certain every compound, and I'll give you those values right now. I'll show those to you. Okay, let's another important thing that you have to remember here is one of those reaction. This is based on using hydrogen as a standard. Okay, so everything is relative to hydrogen electrode. In this case, hydrogen gas, reduction of hydrogen at an electrode. Okay, reduction of hydrogen at an electrode is when hydrogen is 1 molar concentration and at 1 atmospheric pressure, that voltage is regarded as E naught equal 0. So now everything is standard taken as in reference to this hydrogen electrode. Okay, so if our hydrogen electrode, which is called standard hydrogen electrode, also abbreviated as SHE, that produces an E naught value of 0. So next to it, you compare whatever electrode, and that would give you its own standard reduction potentials. Whatever potential you get next to a hydrogen electrode is the standard reduction potential for that electrode. So let's say if I'm reducing copper somewhere, copper 2 plus to copper, and my second electrode is hydrogen, whatever is the E naught next to this, that is my potential for copper. Okay, so hydrogen here, hydrogen electrode acts as a standard or a relative electrode. Example. Now remember, I said there is a reduction half, there is an oxidation half. E naught of the cell is always going to be E naught at the reduction plus E naught for oxidation. Remember that. Okay, E naught of a cell is E naught reduction plus E naught oxidation. And what are these reduction potentials? Let me go a couple slides further and then I'll come back to this. So whenever you have a galvanic cell and you want to identify what is the E naught for that galvanic cell, it's always going to be E naught cathode plus anode. So you take the two E naught values and add those up. Okay. We'll come back to these examples later on. So this is standard reduction potential for different compounds given to you. Okay, different reaction, different reduction reaction that can happen. All of those are given to you right here. For instance, if F2, which is fluorine gas, is being reduced, it will produce F minus, and for that E naught for this particular half reaction is going to be plus 2.87. Okay, similarly, if I pick anything from here, let's say we were talking about copper and zinc, right? We saw those example a lot. So in this case, you see right here copper. So copper 2 plus right here is reducing to copper solid, and the potential for that is plus 0.34. So that is when copper 2 plus is reduced to copper solid, it has a potential of 0.34. Now what's important here is that these are all reduction potentials. So everything here that you see is getting reduced. The higher the value of E naught, the more are the chances of it to get reduced. Okay, so the higher the E naught value, higher is that reaction in this placement, wherever the whatever reaction lies on top is the reaction that is going to happen by itself, or is the reaction that is going to be reduced, is the compound that is going to be reduced. All right, so for instance, if I have a cell, we saw a galvanic cell between copper and zinc, right? So let's identify copper 2 plus. That was a reaction between copper 2 plus and zinc 2 plus. So let's find out where is the zinc 2 plus located. Zinc 2 plus is right here. So zinc 2 plus plus 2 electron changes to zinc solid, and what is the potential for this reaction? It is right here, negative 0.76, and this is plus 0.34. Okay, so if I ask you, these are the two reactions that are happening in a galvanic cell, which will be the oxidation half and which will be the reduction half? Remember, whatever has a higher value, whatever lies on top is the reduction half. Okay, so which one out of these two has a higher E naught value of reduction? Copper, which means copper will be happening as it is and zinc will be opposite of it. Okay, so this reaction is spontaneously going to happen. So copper 2 plus will be adding 2 electrons to form copper solid. So this reaction would be happening. This would be my reduction reaction. And what happens at reduction? Where does it happen? It happens at cathode. So E naught cathode in this case is going to be equal to whatever the value is, plus 0.34. And the unit is volt. Okay. And what would happen to the second reaction? The second reaction, this is given to you reduction, right? Which means if this is reduction, the other has to be oxidation. So it has to be reversed. So whatever lies at bottom is going to be reversed. So you're going to reverse this reaction, which means zinc solid is going to be converted into zinc 2 plus aqueous and 2 electrons. So make sure you do that. Okay, the top reaction stays as is, the bottom reaction is reversed. And what this bottom reaction is oxidation, right? Top is reduction, bottom is oxidation. Oxidation happens at anode. So E naught anode is going to be, now if we reverse the reaction, we also reverse the sign of our E naught value, because these are E naught reduction. What is happening here? This is oxidation. So E naught of oxidation is going to be reverse sign, which means it's plus 0.76 volt. Why? Because this was given to us as negative. We reverse the reaction, so we reverse the sign of our cell as well. Now, if I add this cell, how would you add this cell? We cancel out to make sure there are 2 electrons for each. So 2 electrons cancelled out. So our E for this cell would be E2, copper 2 plus zinc solid will be converted to copper solid plus zinc 2 plus. And what would be E cell here? E for the cell would be E naught cathode plus E naught of anode, right? So E cell would be cathode is 0.34 volt plus 0.76 volt, which gives you a total of 1.10 volts. So this is the E cell, and you see this E cell is positive, which means this is a spontaneous reaction. So we already saw in our first examples of galvanic cell that this reaction happens spontaneously when you connect these two in this form. If zinc is the anode and copper is the cathode, this reaction is going to happen by itself spontaneously. And how can you identify it as spontaneous? By calculating E cell. How would you calculate E cell? You would first identify the two reactions in this chart. Then whatever lies on top is your reduction, is going to happen as it is. Okay, once it happens as it is, that is what reaction happens at cathode. Whatever lies at the bottom is going to be reversed. So you reverse the reaction and you reverse the sign of the E value as well. And then you add the E for cathode and E for anode, and that gives you value of E. Once you have the value of E, if it's positive, it's spontaneous. If it's negative, it's non-spontaneous. And the reverse will be spontaneous. Okay, I hope everybody understands that. So whatever I just said is also written out right here in words. So this tells you that E naught is for the reaction as written. So The E naught value that is given to you right here is for the reaction as written. You cannot just assume reverse is also going to give you the same value. If this is the reaction, this is the E naught value. If you reverse the reaction, you reverse the E naught value. Okay. Next, the more positive E naught, the greater the tendency for a substance to be reduced. Like I said, the more positive, the reaction will happen as it is, and this is a reduction reaction. So the substance will get reduced. The half cell reactions are reversible. So if you are doing this reaction as in this form, this reaction can also happen in reverse form. Just depends on what is the other reacting species. If it lies under it, it is going to happen as it is. If the other reactant is over it, the reaction would be reversed. So these reactions are reversible. If you reverse the reaction, you reverse the sign of E naught as well. The sign of E naught changes when the reaction is reversed. Changing the stoichiometric of a half reaction does not change the value of E naught. What that means is, let's say if you saw certain examples we did before where to balance the total number of electrons, we multiplied the reaction by a number. So if I multiply this reaction, let's say bottom one, we don't have to in this case, but let's say for certain example, I have to multiply this by 3. You do not change the E naught value. It does not mean that the E naught value now is going to be 3 times 0.76. Okay, so remember, you can change this and multiply with the stoichiometric coefficients by whatever number, but E naught value you do not change. E naught stays the same. It does not mean that now if you have 3 zinc solid getting converted to zinc 2 plus, it's going to produce 3 times the electrical energy. That's not true, because it's a continuous process, remember. So one would produce this much, the second would produce this much, but this electrical difference is going to be used up at the same time. Okay, so what you want to do is just E naught cell, which is just reverse the signs. That's it. You do not multiply the E naught values, you do not divide the E naught values by anything. All right, let's try one example. First is a simpler example. Draw a diagram, show the balanced equation, and write the notation for a voltaic cell that consists of one half cell with Cr bar in Cr NO3 3, so chromium nitrate, another half cell with silver in silver nitrate solution, and the potassium nitrate salt bridge. Measurement indicates chromium electrode is negative relative to silver electrode. So in this case, we have to first draw a galvanic cell, right, and write down the cell notation. So first thing we have to do is we have to identify what are the two half reactions that will happen in this case, right? Okay, so the two half reactions we know here is, first is chromium, sorry, ignore this. So the first step is chromium is getting converted into chromium nitrate, and the next step is silver nitrate. So those are the two reactants and products that are involved. We don't know if chromium is converting to chromium nitrate, or is that reverse reaction, right? So first step we'll have to do is we'll have to identify which direction is the reaction going. Only thing you should know is you should identify what are the reactants and products involved with respect to ions. That's it. Okay, we don't care about, in this case there is chromium and Cr ion, silver and silver ion. We don't care about nitrate here. Why? Because these are spectator ions, they are not getting converted, right? The charge that is changing is between these two. The oxidation number of these two metal is what is changing, right? Okay, so what would happen? We know that Cr is, what would be the oxidation number on Cr here? It's by itself, it's the elemental form, so it's going to be 0. So this is 0. The other is Cr nitrate. Now if you go and use the rules that we just saw for oxidation number, your answer will not come out to be correct in this case. So nitrate is like nitrogen and phosphorus, like we saw. They belong to the group number 15, right? But usually we say that is like +3 charge, -3 charge, but it's not always true. So nitrogen here is one of those exceptions. So don't use that rule. What you can do when you see nitrate essentially is, when you see nitrate, what is the charge of nitrate? ion, polyatomic ion, if you know, it should always be NO3 minus. So each of this would carry a -1 charge. So if I'm trying to identify for the total charge of chromium in chromium nitrate, what would it be? I can say chromium is, let's say, 1 Cr, right? Plus each nitrate carries a total charge of -1. So I have 3 of those. So 3 times -1 is equal to 0. Why 0? Because in total it's a neutral compound, so that rule still applies. So what is the total charge of Cr? Cr -3 equals 0, meaning Cr is plus 3. So what's happening here? Cr ion, which is 0, Cr is getting converted to Cr ion, which is plus 3. I don't know if it's going in this direction or reverse. We'll figure that out based on our chart. Next thing I know is between silver and silver nitrate. Now same thing apply here. Nitrate, ignore those rules, go by silver. Silver nitrate would be Ag plus. Now we will go to our chart. We'll find these in our chart. Let's look for Okay, so let's look for our reactant and products on our chart. We are looking for one is Cr, another one is silver. So let's look for Cr first. Cr is Cr plus 3 and Cr. Okay, those are our reactants and products. Now remember, Cr can exist as multiple forms. Each of those can exist as multiple ionic forms, right? You know, transition metals can have multiple charges. So you are looking for the specific kind that we want, okay? For instance, I see right here is my silver. So silver is silver plus 2 silver, and that's exactly what I'm looking for. You see silver is also present right here with silver AgCl. I'm not looking for this. I'm looking for this specific reaction. And where is it? It's right here. It's the value is given to me. Okay. Next, I'm looking for chromium, Cr3 plus. If you go through your chart, you'll find it right here. Oh, and charts will be given to you. I forgot if I mentioned that in the video already, but you don't have to memorize this, of course. Chart will be given to you. This is Cr3 plus 3 electrons is getting converted to Cr. So that means my reactions right here. This is at the bottom. So which reaction will I reverse? I will reverse the bottom reaction. The top reactions happens as is. So let's write our reactions first. So the top reaction will happen as it is, which is silver ion aqueous. One electron will be converted into silver solid. E naught, meaning this is happening by itself. So this is a reduction reaction. Where does reduction happen? At cathode. So this is my cathode reaction. Next, I need my reduction oxidation reaction. Whatever is at the bottom will be reversed. So let's reverse that. That would be Cr. So Cr, sorry, let me erase that. So this is Cr solid. We are reversing the reaction, is getting converted to Cr3 plus 3 electrons. So you can write it as is, it's given to you. And now it's reversed, meaning this is anodic reaction. This is happening, this is oxidation, right? Loss of electrons. So this happens at anode. So remember, whatever's on top of the chart happens at cathode. Whatever's at the bottom of the chart happens at anode. That's it. Okay, whatever you reverse is happening at anode. So now these are my two half reactions. Now the question asked me, first thing, write a balanced reaction. So let's balance it out. How do I balance it? You will balance each half reaction by itself. So silver plus is changing to silver. How do you balance it? Go by the rules. Okay, the first rule, balance every element other than oxygen, hydrogen. One silver, one silver. Balance oxygen. I don't have. Balance hydrogen. I don't have. Balance charge. How much is the charge on this side, on the reactant side? +1 -1 gives me a total charge of 0. This is also 0. So charge is balanced. So this half is balanced. Next half, balance every element other than oxygen, hydrogen. One chromium, one chromium. Perfect. Balance oxygen, I don't have. Balance hydrogens, I don't have. Balance the charge. What is the total charge here? 0. Total charge on the other end, +3 and -3. Right? Because 3 times -1. So total charge is balanced. But also one thing I can tell you, if the reactions written out right here in this, they are balanced reactions. So you can kind of like skip this step. But if you want to be extra careful, you can. But these reactions that are listed right here will always be balanced. the half reactions would always be balanced. Okay, for instance, you can see right here, this is a balanced half reaction. So your half reactions will always be balanced if they are written in this chart. But anyways, we have to write an overall reaction. The last step of overall reaction is you should balance the total number of electrons in both the reaction. How many electrons here? 1, here 3, which means I have to multiply the top reaction by 3. Does not mean you multiply the E naught value. Remember that. Okay, E naught stays the same. Okay, so if I multiply this by 3 and I start adding up, that would give me 3 silver ions, aqueous. I have 3 electrons here, 3 electrons here, they get cancelled. Plus 1 chromium solid is getting converted to silver solid. What did I forget here? 3. This is 3 silver. Plus 1 Cr ion. 3 plus ion. Okay, that is my balanced overall reaction. Now the question was also to write the notation for galvanic cell. What is the notation? Remember, you always put anode on the left, then a bar, then cathode. So this is salt bridge and then cathode. So let's write down what's happening at anode. At anode, Cr solid is converting to Cr3 plus, which is aqueous, separated by the salt bridge. And then the reaction at cathode. What's happening at cathode? Silver ion, which is Ag plus, is getting converted into Ag solid. So the reactant and product should be separated by single bar, and the cathode and anode should be separated by double bars. Now in this case, you can see right here, there's a solid, and the question also told you the electrode is chromium here, it has Cr bar, it has a silver bar, which means these are going to act as my anode and cathode respectively. So I don't need graphite here or platinum here. In case you do, if both are ionic in nature, you can put graphite or platinum, whichever one you want. Just make sure you put both on both the corners and you'll get the points for that. All right, that's your final answer for this question. If the question asked you calculate E naught cell, which the question has not in this case, what would be the E naught cell value? Remember, E naught cell would be E naught cathode plus anode. What is the cathode value? Cathode value stays as it is, which is plus 0.80, plus anode value is, if it was negative 0.74, it would become positive 0.74, because we flipped the reaction, we flipped the sign, plus 0.74, and you add this up and that would give you 1.54 volts. So that would be your E for the cell if the question asked you, but it's not. Okay. All right. Moving on. It's shown you right here as well. So if I ask you, I'll probably just ask you this notation. I'll of course not ask you to draw a graph or make a figure. What I can ask you is I can give you a figure and ask you to draw direction of electrodes and like name the electrodes, direction of electrons, how they're moving. Okay. Okay. Let's move on to the next question. Okay. What's the question? Balance the following skeleton ionic reaction and calculate E naught cell to decide whether the reaction is spontaneous or not. Okay, and it's happening in acidic solution. So balancing part, I think you guys should be very familiar by now. But let's just balance our reaction. Manganese is getting converted. Manganese 2 plus is MnO4 minus, sorry, and bromine liquid is getting converted to Br minus. So if I start balancing, I have, sorry, I should, oh, don't do that. Okay. Ignore the answer that you're seeing at bottom, but let's start balancing our reaction. So if I'm balancing like this, I would have 1/2 would be manganese 2 plus is getting converted to MnO4 minus, and the second half would be Br2 liquid is getting converted into Br minus aqueous. So if I start balancing this, what do I have? We'll balance one reaction at a time. Mn2 plus is changing to Mn, 1 Mn on this side, 1 Mn on this side. Next I balance oxygen. I have 4 here, so I add 4 water, 4 H2O. And then to balance out Oxygen's balance. Next step is balance hydrogen. To balance hydrogen, I add protons. I have 8, so 8 protons. I'm going faster because I'm assuming you guys have practiced the previous video. Next I have protons. Next I balance charge. What's the charge here? I have 0 for water, so 4 0 plus 1 manganese, so 2 plus, which gives me a total charge of plus 2. Okay. Next I have this. I have 1 negative 1, so 1 times negative 1 plus 8 times positive 1, which gives me a total of positive 7. So to balance it out, I have to add electrons. Which side? I add electrons here to reduce the positive charge, which means I add 5 electrons to make a total charge would become plus negative 5, which would be a total of plus 2, which means my charge is balanced on both the sides. Next, I balance the second reaction, which is Br2 to Br minus. First, let's balance all the elements other than oxygen, hydrogen. 2Br here, so 2Br here. Oxygen, I don't have. Hydrogen, I don't have. Charge is what I balance here. What is the charge on this side? 0. What is the charge on this side? Negative 2, because I have 2 of these, right? 2 times negative 1 gives me negative 2. I can only add electrons, so I'll add electrons on this side. How many? 2 electrons. That would make this a total of negative 2, negative 2, balanced. All right, perfect. What's the next step? We balance the total number of electrons. So how many electrons on this side? 2. How many on that side? 5. Meaning I have to multiply this reaction by 2 and this reaction by 5 to balance the total number of electrons. So if I add these two, that would give me 2 half reactions, which would be 8 water, because I'm multiplying it by 2, plus 2 manganese ion, give me 2 permanganate ion, plus 2 times 8 is 16 protons, plus 2 times 5 is 10 electrons. Next I add this reaction, which is 5 times 2, so 10 electrons, plus 5 Br2, changing to 10 Br minus. Now we add everything up to get to our final reaction. Based on this, first thing we can identify is which reaction is happening at cathode. This is loss of electrons. So this is loss of electrons. So sorry, Leo, loss of electrons. This is oxidation. So this is my oxidation half. Oxidation happens at anode. This is happening reduction. So GER. Where does this happen? This happens at cathode. Okay. But you also have another way. If you, the question, let's say, didn't ask you to balance it out, how would you do it? I'll show you that as well. But what's happening here? We will add the two reactions up. So electrons and electrons will get cancelled. My final reaction would be 8 water, nowhere else. So 8 water plus 2 manganese ion, nowhere else, plus 5 Br2, nowhere else. Br2 again, remember it's a liquid, so I'll put liquid right here. Changes to 2 MnO4 minus, plus 16 protons, plus 10 Br minus. Perfect. All the ions aqueous, 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 and water is liquid. All right, that's my balance reaction. Now the question was asking, is this reaction spontaneous or not? So if this is that reaction that is happening, it is telling me this is happening at anode, this is happening at cathode. So what do? We go back to our chart and we look for the values of our two reactions that are happening. Okay, don't do that. Okay, ignore the answer that you're seeing at bottom, but let's start balancing our reaction. So if I'm balancing like this, I would have 1/2 would be manganese, 2 plus is getting converted to MnO4 minus, and the second half would be Br2 liquid is getting converted into Br minus aqueous. So if I start balancing this, what do I have? We'll balance one reaction at a time. Mn2 plus is changing to Mn. 1 Mn on this side, 1 Mn on this side. Next I balance oxygen. I have 4 here, so I add 4 water, 4 H2O. And then to balance out oxygen's balance, next step is balance hydrogen. To balance hydrogen, I add protons. I have 8, so 8 protons. I'm going faster because I'm assuming you guys have practiced the previous video. Next I have protons. Next I balance charge. What's the charge here? I have 0 for water, so 4 0 plus 1 manganese, so 2 plus, which gives me a total charge of plus 2. Okay. Next I have this. I have 1 negative 1, so 1 times negative 1 plus 8 times positive 1, which gives me a total of positive 7. So to balance it out, I have to add electrons. Which side? I add electrons here to reduce the positive charge, which means I add 5 electrons to make a total charge would become plus negative 5, which would be a total of plus 2, which means my charge is balanced on both the sides. Next I balance the second reaction, which is Br2 to Br minus. First, let's balance all the elements other than oxygen, hydrogen. 2 Br here, so 2 Br here. Oxygen, I don't have. Hydrogen, I don't have. Charge is what I balance here. What is the charge on this side? 0. What is the charge on this side? Negative 2, because I have 2 of these, right? 2 times negative 1 gives me negative 2. I can only add electrons, so I'll add electrons on this side. How many? 2 electrons. That would make this a total of negative 2, negative 2, balanced. All right, perfect. What's the next step? We balance the total number of electrons. So how many electrons on this side? 2. How many on that side? 5. Meaning I have to multiply this reaction by 2 and this reaction by 5 to balance the total number of electrons. So if I add these two, that would give me 2 half reactions, which would be 8 water, because I'm multiplying it by 2, plus 2 manganese ion, give me 2 permanganate ion, plus 2 times 8 is 16 protons, plus 2 times 5 is 10 electrons. Next I add this reaction, which is 5 times 2, so 10 electrons, plus 5 Br2 changing to 10 Br minus. Now we add everything up to get to our final reaction. Based on this, first thing we can identify is which reaction is happening at cathode. This is loss of electrons. So this is loss of electrons. So sorry, Leo, loss of electrons. This is oxidation. So this is my oxidation half. Oxidation happens at anode. This is happening reduction. So GER. Where does this happen? This happens at cathode. Okay. But you also have another way. If you, the question, let's say, didn't ask you to balance it out, how would you do it? I'll show you that as well. But what's happening here? We will add the two reactions up. So electrons and electrons will get cancelled. My final reaction would be 8 water, nowhere else. So 8 water plus 2 manganese ion, nowhere else, plus 5 Br2, nowhere else. Br2 again, remember it's a liquid, so I'll put liquid right here. Changes to 2 MnO4 minus, plus 16 protons, plus 10 Br minus. Perfect. All the ions aqueous, 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 and water is liquid. All right, that's my balance reaction. Now the question was asking, is this reaction spontaneous or not? So if this is that reaction that is happening, it is telling me this is happening at anode, this is happening at cathode. So what do? We go back to our chart and we look for the values of our two reactions that are happening. Okay. Okay, so we go to our chart to look for our two reactions. I just rewrote those reactions right here from what we just did. So this is happening at anode. We know that this is oxidation reaction. This is happening at cathode. This is a reduction reaction. The question is asking, is this reaction spontaneous or not? How do we know that? We are going to figure out what would be the potential if this reaction is happening at cathode and if this reaction is happening at anode. Okay, we'll assume this is what is happening. Okay, and then we'll calculate E of cell by adding E of cathode plus E of anode, and that would tell us if this value is positive, it's spontaneous; if it's negative, it's non-spontaneous. Okay, so let's find these two reactions on our chart. We have Mn2 plus changing to MnO4 minus, so that reaction's right here, MnO4 minus and Mn2 plus. Okay, and the second reaction is between Br2 and Br minus. So let's look for Br2 and Br minus right here. So that's my next reaction. Now, if I was doing this reaction by itself, I know that this reaction would happen by it as it is, and this would be flipped, right? But the question has already told me what's happening. The question is telling me this reaction is happening in this form, which means this has been flipped. The top reaction has been flipped. So just from my experience of doing these questions, right, we know that if the top one is flipped, the reaction is not going to happen. It is non-spontaneous, right? But we have to prove it by showing our numbers. So let's prove that. So we know the answer to our question already now, that the top reaction is being flipped here. Usually we flip the bottom, correct? So in this case, if top is flipped, what if I flip this reaction, my E naught will be flipped. So E naught would be negative 1.51 volts. E of cathode, this reaction is happening as it is, Br. So we are going to keep the same sign, equals plus 1.07 volt. Now I add these two values up, which is 1.07 plus plus negative 1.51 volt, right? That would give you a value of negative 0.44 volts. We know that our value of E cell here is negative, which means this reaction is non-spontaneous. That's our answer, and that's how you're supposed to show your answer. Okay. But if the question was different, if it was worded different, if the question was asking these are the two reactions, can you tell me what happens at anode, what happens at cathode, then you know that the top reaction should happen as is and the bottom would be flipped, and that's when your E cell will come out to be positive. Okay, I hope you guys are understanding the question, the difference between the two scenarios. Okay, the question right now, this is the answer that you give me. Okay, all right, let's try the next question. These questions are very easy as long as you understand that you go look into the chart. Once you have the values in your chart, you just know the top one happens as is, the bottom one will be flipped. Okay. Okay. Now in the next part, it's saying predict what will happen if molecular bromine is added to a solution containing NaCl and NaI at 25 degrees Celsius, assuming all species are in their standard states. Okay, so now the question is already telling me this is what's happening. We have molecular bromine, okay, and a solution containing NaCl and NaI. Assume all species are in standard states. Now the question is asking what will happen, meaning it's asking us which direction will the reaction go. Okay, now again, if you see this question by itself, let's say you're seeing this question in the final exam, you would not know what chapter this question is from. Okay, the question could be from equilibrium. Chemical equilibrium also tells you which direction will the reaction go. Thermodynamics also tells you which direction will the reaction go. Electrochemistry also tells you which direction will the reaction go, right? So you have to know based on what values are given to you, can you identify which direction will the reaction go. Okay, there's no equilibrium constant given here, so we know it's not an equilibrium question. There is no thermodynamic information given to us, so we know that's not the answer. There's no other information given to us, so there's a probable chance we can use the sheet that would be given to you, which has E naught potential values, E naught reduction. So if you have those, using that you can predict the direction. Okay. All right. So now what are the question? What are the two scenarios? We are given Br2. So meaning Br, the one reaction that is happening is between Br2 will be converted to Br minus. That's the only scenario. Okay. What if you balance this reaction? We are going to look for this reaction in our chart. We don't have to balance it since the chart gives us balanced reaction. Next, the other reaction that would be is between Cl and Cl minus, right? So I know Cl minus is getting converted because I have Cl minus. So Cl minus is converted to Cl2, and then I have I minus, which is I minus is converted to I2. Now I have to find these in my chart, and then I can tell what is going to happen in the reaction. Okay, so let's go back to our chart. Okay, so I just pulled up the chart right here. I know it's a little small, but you can pull up the chart separately for you guys, and we'll look for these reactants and products. Okay, so I'm looking for Cl minus and Cl2. I see it right here. Cl2 is right here with Cl minus. Next, I'm looking for Br2 and Br minus. Br2 and Br minus is right here. Okay. Next, I'm looking for I minus and I2. I is right here. I minus and I2. Okay, so now based on this, I know that which reaction has to happen by itself. This reaction, these reactions have to happen in this direction. The question is telling me, right? I don't have any Cl2 to go to Cl minus. I just have Br2 to Br minus, so that is happening by itself. So this reaction is happening. If this reaction is happening by itself, what is the other reaction that can happen? This in reverse, right? This, if I combine these two, I cannot reverse the top reaction. Remember, you cannot reverse the top reaction. So that cannot happen. Since the second reaction is happening as it is, E naught of this is going to be 1.07, right? And this can be reversed because this is happening at the bottom and I am looking for reverse reaction. So that would be E naught would be negative 0.53. So which reaction is going to happen based on the question? The question says assume all these species are present. Predict what will happen. In this case, Br2 will get converted to Br minus and I minus will get converted to I2. So that would be your prediction. This reaction is going to happen and Cl minus is going to stay as it is. Okay, Cl minus is not going to be used up during this reaction. It will not be involved. Why? Because it's not possible. We can't do reverse because we don't have Cl2 to begin with, right? So these are the values as you look from the chart. And now based on this, we see that Br2 will be able to oxidize I minus but will not oxidize Cl minus. Therefore, the only redox reaction that will occur under standard state condition appreciably, meaning spontaneously, would be this. I minus would be converted to I2, Br2 will be converted to Br minus, and this would be your final reaction. Another rule that this brings us to is the diagonal rule, which is fairly easy to understand. Under standard state conditions, any species on the left of a given half cell reaction will react spontaneously with the species that appear on the right of any half cell reaction located below it. Okay, in the table, that is high electron E naught reactions will oxidize a lower E naught reaction, right half reaction with greatest E naught above the other. What does this mean? Let me show you. Okay, so the diagonal rules said that under standard condition, any species on the left of a given half cell reaction, so if this is the species, let's say, it will react spontaneously with species that appear on the right of the half cell in and below it, in a reaction below it. So this will react with anything spontaneously that's on the other side of the reaction. So if let's say I'm picking up these two reactions between Cr, this reaction and this silver reaction, okay, what is the spontaneous reaction? Whatever is on the top and the left side, that is your reactant, is going to react with whatever is diagonally below it. So whatever's on the left would react with whatever's on the right side of the reaction of a reaction below it. So that's the diagonal rule. So this reaction would happen as it is. This would be flipped. So essentially one reactant would be this and second reactant would be the one diagonally present below it. Easy? Same thing. Let's say if I picked whatever reaction you want. I pick this reaction, oxygen, and then I pick this reaction right here between iron. Okay, so if this is one of my reactant right here, oxygen and water, my second reactant with this would be diagonally under it, meaning on the right side of the arrow and below it. Okay, so it always has to be below and it has to be right. That's what would tell you if it is spontaneous or not. So it essentially means the same thing. If you understand this, that top reaction happens as it is, the bottom will be flipped. So if this is flipped, this would be a second reactant. All right, I hope this makes sense. We'll move on to another couple questions. So let's try this question. You can pause the video. A galvanic cell consists of magnesium electrode in a 1 molar magnesium nitrate solution. So again, magnesium would be Mg0. Magnesium nitrate would be Mg2 plus. Remember, nitrate, don't even think about doing the rules. Just go by. Nitrate has a -1 sign. Okay, each nitrate. And a solution of silver in silver nitrate. So one of them is silver silver 0, another one is silver plus. Calculate the standard EMF for the cell. Very straightforward question. What you're going to do is you're going to look for these values in your chart. If you look for the values in your chart, you will find, let me pull up the chart again. Okay, so we're looking for silver and silver plus and magnesium 2 plus. So silver plus is right here. Silver plus is changing to silver right here, plus 0.80. Then magnesium and magnesium 2 plus is, where is magnesium? Right here at the very bottom. So based off of this, the question is asking calculate E naught of the galvanic cell. So what would be the E naught of the galvanic cell? It doesn't tell us which direction is the reaction going. So we have to figure out what direction, which we know from this rule, the top stays at it is, bottom is flipped, right? So either top stays at it is or diagonal rule, whatever works for you. So this is one of the reactant. The second reactant is diagonally under it, second reactant. So you have to flip this reaction. So based on this rule, I know this reaction will stay as it is. So my E naught, top is always cathode, remember, would be 0.80 plus 0.80 like the sign says. What will happen at the E node? At the anode, this reaction will be flipped, meaning my value will be flipped. So it will become E naught equal plus, it will flip the sign, right? Plus 2.37. So what would be E of the cell? E of the cell will be E of cathode plus E of anode, or E naught. So E of cathode is 0.80 volt plus 2.37 volt, which will give you a total of 3.17 volt. So your final answer is going to be 3.17 volt. So these questions would be as straightforward as this. It doesn't always have to be very difficult. Okay, we went over the difficult questions before, but the question could be as simple as this. Okay, moving on. It's also solved for you right here. Moving on, we go to the next question. A voltaic cell houses the reaction between aqueous bromine and zinc metal. This is given to you. E of the cell is this. Calculate E naught for bromine given that E naught for zinc is 0.76 volt. So in this case, E for the cell is given to us. E for one of the electrodes is given and second electrode is being asked. So how would you do that? You have to first identify what is happening at cathode, what is happening at anode. And how would you identify that? Remember, cathode is where reduction happens, anode is where oxidation happens. So we are going to identify the two electrodes. First is Br2 is changing to Br minus. So that's my one reaction. Br2 is changing to Br minus. Balance it. Br2, 2Br, now balance the charge 0 on this side minus 2 on this side, so I add 2 electrons on this side. If I add 2 electrons here, that means this is addition of electrons, so gain of electrons, meaning this is reduction. So where would this happen? This would be happening at E naught, whatever is the BR is E naught for cathode, because it's reduction reaction, which automatically makes the other one anode, oxidation, but we'll confirm. Zinc solid is changing to zinc 2 plus, which is aqueous. Again, what is the charge here? 0. What is the charge here? Plus 2. So if this is plus 2, to balance the charge, I need 2 electrons on this side. Again, this is loss of electrons. Loss of electron is oxidation. Where does oxidation happen? Oxidation happens at anode, which confirms this is the reaction that's happening at anode. So E naught for zinc is given to us. Again, this is always, remember, these are always reduction values. Okay, so what is getting reduced? This is getting reduced. What's given to us is E naught for zinc. Okay, which means if this is negative 0.76, this would be, for anode, it's going to be oxidation. So this is reduction half. Remember, whenever E naught is always standard for reduction potential. Its name is standard reduction potential. So this is reduction potential given to us, which means we have to flip this sign. So E naught for anode is going to be plus 0.76 volt. Why? Because this is happening at anode. Anode is the bottom one. Bottom one is always flipped. E for cathode is what we have to find out. E for cell is given to us 1.83, which is cathode plus anode. You can just plug in the numbers. So 1.83 volt equals cathode is what we have to find, and plus, sorry, anode is 0.76 volt. So what would be cathode? Cathode would be, I'm just going to plug it right here. Cathode would be 1.83 volt minus 0.76 volt, which would give you a final answer of 1.07 volts. So your answer for this, E naught for bromine, remember this is reduction, and what the question is also asking you for reduction, so E naught would be 1.07 volts. That's exactly how the question can be flipped. One of them can be given to you, the other one would be asked for, or the question would be simple, like figure out what is E naught for cell. Okay. Okay, let's try another question. It says using half reactions to write a spontaneous redox reaction. These are the two reactions given to you. Using the half reactions to write a spontaneous redox reaction. The question is worded perfectly. The question is asked, can you write down the spontaneous redox reaction for this? So what would be the redox reaction? These values are given to you. Now, instead of looking in the chart, you can just look right here. This is given to you. You know, whichever one is the higher value, whatever E naught value is higher, that stays as it is. The other one is flipped, correct? Which one is the higher value out of these two? This is the higher value. So this reaction will happen as it is, which means silver plus aqueous plus electron will change to silver solid. This reaction will happen as it is. So E naught, this is cathode, would be 0.80 volt. The other reaction, on the other hand, will be flipped. So we would flip that and it would become Sn solid will change to Sn2 plus 2 electrons. And E naught in this case is also going to be flipped. This would be anode. Remember, always anode is flipped. Okay. Now the question didn't ask for us for E cell. It is only asking for us write the spontaneous redox reaction. So we'll write the spontaneous. We have to add these up, but before that, let's see, everything else is balanced. Everything is balanced. What's not balanced is the number of electrons on both reactions. Here I have 1, here I have 2, so meaning I have to multiply this reaction by 2. If I multiply this, it gives me 2 silver aqueous electrons, 2 and 2 electrons get cancelled. 1 silver, oh sorry, tin solid produces silver solid, which is 2, don't forget the 2, plus 1 Sn2 plus, which is aqueous. So that would be my spontaneous redox reaction. That's exactly what the question is asking, and that's your answer. If there was a part B to this question, what is the E for the cell? E for the cell would be E of cathode plus anode. So add these two up, which would give you 0.94 volt. But the question's not asking here. Okay, that's how you figure out what would be your spontaneous reaction. So now you know how spontaneity of a reaction can be determined based on E of the cell. Right? Okay, last part is we found out before that a reaction can be spontaneous. We can tell that based on the sign of G and based on the sign of E, which means both of these values have to be somehow related to each other, right? So both G, free energy, and E of the cell helps us predict spontaneity of a reaction. For a chemical reaction, a negative delta G value means a reaction is spontaneous. For an electrical system, E of the cell has to be positive. That means the reaction is spontaneous. Okay. So for you, at standard condition, how are these two related to each other? Delta G naught is equal to negative NF E naught of the cell. Okay, G naught is at standard condition free energy. E naught is, electrical potential difference for the cell at standard conditions. What is N? N is the number of moles of electrons that are transferred. Okay, now how do you figure out number of moles of the electrons? This is coming from balance reaction. When you balance the two reaction, you cancel out the total number of electrons, right? When you are adding at the final step, when we're adding the two reactions, we cancel out the total number of electrons. That is the total number of moles that will go here. Okay, what is F? F is a constant called Faraday's constant. Its value is given to you right here. 1 Faraday is 96486 coulombs per mole of electrons. So this would give you moles of electrons, this would give you coulombs per mole, and this would give you the electronic potential in volt. Okay, now these questions would be very straightforward. One of those would be given to you, and all rest of the information would be given to you. One of these would be missing, and the question would be asking to solve for that. Only important thing here is make sure the units are correct. Again, you don't have to memorize this. I'll provide you this equation. So only thing you have to remember is that when to use this. And second thing is make sure you're matching up the units. The units should be matching up. Okay, the next last thing is that you should not make a mistake when figuring out what is the value of N, number of moles. Okay, a lot of times people make mistake in that. Number of moles is when you cancel them out, whatever total number after multiplying the reaction, when you cancel it out, that is the number that you use after multiplication. Okay, let's quickly try a couple questions. Okay, first question is right here. Calculate delta G naught for the following reaction. E naught is given to us. Okay, what is the relationship that we know that relates E naught and G naught? There's only one relationship that we are aware of. We know that delta G naught for us is equal to negative NF delta E naught for the cell. E naught for the cell is given to us. Delta F is the Faraday constant, which we are already aware of, so we know what it is. Lastly, what we need is N right here. And what is the value of N? We'll have to solve for it. Okay, how do you solve for it? You balance your chemical reaction. Okay, so here aluminum is changing to Al3 plus, gold 3 plus is changing to gold. You don't just balance one of the reaction, make sure you're balancing both the reactions. Okay, so Au3 plus is changing to Au, and silver, I'll write it right here. Aluminum is changing to aluminum 3 plus. So if I'm balancing it out, one aluminum, sorry, this is gold, one gold, one gold. Do I have any oxygen, hydrogen? I don't. So I move on to the next step, which is balancing the charge. What is the total charge on one side of gold plus? It's plus 3. This is 0, which means I add 3 electrons on this side. That would make a total charge of 0 right here. How about this? This is one aluminum, no oxygen, no hydrogen. Charge here is 0, charge here is +3. So to cancel the +3 charge, I need 3 electrons on this side. Which means if I'm adding these two reactions up, I have 3 electrons here, 3 electrons here. So my reactions are balanced. I don't have to multiply any of these reactions by anything. So the total number of electrons that I will be canceling out here would be 3. So what is N? N is 3 moles of electrons. Okay. So delta G naught is going to be NF, which is negative 3 mole of electrons times 96485 coulomb of energy over 1 mole per mole of electron, right? That was the F value of F, times one thing, E naught cell, which is 3.16 volt. Okay, this would give you mole and mole got cancelled, and your final answer is going to be in negative 914,678 coulomb times volt, right? Now, one thing I forgot to mention in the previous slide is that 1 joule is equal to 1 coulomb volt. So essentially you can just cancel this out. Coulomb times volt, like you can use this conversion factor to go from joules to coulomb volt and vice versa. So if I cancel this out, that would give me essentially the same number. Now if we are going by right number of sig figs, what is the number of sig figs given to us in question? 1, 2 and 3. This is an exact number, so we don't care about sig figs from here. This is 3, so I have to end my answer right here, which means it's going to be negative 915. Now I can't end my answer right here, right? So it has to be 915. Either I convert this into kilojoules, or you can also give me the answer as negative 9.15 times 10 raised to power 1, 2, 3, 4, 5, 10 raised to power 5 joules. That would also work. Okay, any of these two would work. Okay, so just make sure we are cancelling out this part right here. 1 joule is equal to 1 coulomb volt. That's the part that I forgot to mention before, because sometimes if the options are in joules or kilojoules, then you have to convert it into this. But if you give me the answer in coulomb volt as well, that would do. But most of the times, if you guys know, the unit for free energy should be joules or kilojoules. It should be unit of energy and not coulombs. Coulombs is more like electrical E cell, right? Okay, fairly straightforward question. Moving on to next. This is where things kind of get a little bit tricky if a lot of information is not given to you. So question is calculate Gibbs free energy for the following reaction. And that's it. That's all the information given to you. Now, if you think this is a thermodynamic question, you're partly wrong. Why is that? Because if you go by thermodynamics, you won't be able to find the answer for this. Why? Because again, we don't have any information. Usually in thermodynamics, if it's asking for Gibbs free energy for a reaction, it would give you G for each of the reactants and products, right? There's no information given to you here. Only information that you have here is that you have a chart which has E naught values for it. So from the E naught, you can solve for E of the cell. And from the E of the cell, you can use this formula, delta G equals negative NF E naught cell, right? And that's how you can get the value of Gibbs free energy from here. So usually if no information is given to you about spontaneity or energy to solve for the final answer, it most of the times mean it's coming from, it's a question of electrochemistry. Okay, why? Because that information is always given to you. The chart will always be provided to you for reduction potentials. So what you're going to do is, I'm not going to solve this for you, but I'll give you the hint of how to do this question. You're going to figure out Br2 is getting converted to Br minus, I minus is getting converted to I2. You're going to look for these two reactions in the chart, figure out what would be the E of the cathode, E of the anode, then solve for E naught of the cell. Once you have E naught of the cell, you're going to balance the two reactions to figure out what is moles. Once you have moles, you're going to use E cell and moles multiplied by Faraday constant to figure out what is G naught, and that would give you your final answer. All right, so you should be able to solve for this question by yourself with the information that you already have. Okay, the last part we are going to discuss in this chapter is how E naught cell is related to equilibrium constant. Like I said, if we begin with chemical equilibrium in this uh, course, general chemistry 2, it does not leave us till the end of the course. So right here you see that we just saw that how G naught is related to E naught. Similarly, we know that G naught is related to equilibrium constant. We saw that in thermodynamics that delta G naught is equal to minus RT ln K. We can use these two relationships, and if we rearrange it, that would give us this relationship between E naught and K. So E naught of the cell is equal to RT over NF times ln K. At standard conditions, if you know, at standard conditions, R is always going to be 8.314. Temperature would always be 298 Kelvin. What would be F? We know Faraday constant is always also a constant term which is given to us. So if you plug in these values, only unknown numbers here are ln K and N. So if I plug in those values, that would give you this right here. E naught of cell is equal to either 0.0257 volt over N times natural log of K, or 0.0592 volt over N times log K. So you can use either of these equations, or you can just go with this equation on top as well, whatever you feel comfortable with. I will be providing you most probably in the exam this top equation and the very bottom equation. So you can just not use the L and K. Don't worry about it. It would be always in log since it's easier to work with. Okay. So this is a relationship. These are the two relationships that essentially relate potential of a galvanic cell with the spontaneous equilibrium constant or equilibrium constant of a particular reaction. So now essentially we know their G naught, E naught, and K are interrelated. They are related to each other. For a spontaneous reaction, G naught is always less than 0. K is always greater than 1, right? We know that from chemical equilibrium. And we just saw today that E naught for a cell for a spontaneous reaction is always a positive value. So K and E, they follow a positive trend, and G always has a negative sign to the value of E. So G and E are always opposite of each other. Okay, so if this is less than 0, E is always greater than 0. For a non-spontaneous reaction, delta G naught is a positive value, so always greater than 0. E naught is always a negative value, less than 0. And K is also less than 1. And at equilibrium, delta G naught is equal to 0, K is equal to 1, and E naught is equal to 0. So those are the parameters at standard condition for delta G naught, K, and E naught whenever we are talking about a reaction at equilibrium or spontaneity of a reaction. Okay, and these are the three relationships that relates all of them together. So G naught related to E naught using this, G naught is related to K using this, and E naught is related to K using this. So essentially you can relate all these three in whatever form. The questions are going to be fairly straightforward. One of those would be given to you. The next thing will be asked. So you should just know which relationship to use when, and that should be giving you the final answer. Okay. So next few questions are going to be straightforward. We are just going to plug in the numbers in equations. So I'll just go through those questions, and if you want, you can just every question pause the video, try to solve it by yourself. Okay. Let's try question number 1. So the question says, determine the Kc for the redox reaction. The reaction is given to us right here. E naught is given to us. So we have to basically solve for equilibrium constant using E naught. What is the relationship that we know for this particular reaction? We know that E naught of a cell is equal to 0.0592 volts divided by N times log of K. So essentially I will give you this expression. Only thing here is you have to just know when to use it. So this is my Kc I'm solving for. Do I know N? I don't, but I can solve for it from this equation. What is E naught for the cell? E naught is already given to us in question. Okay. How can we solve for this? Now, same concept. You have to first divide this equation into two halves, balance the reaction. So first half would be BrO3 minus changing to Br minus, 6I minus changing to I2. Then balance the reaction to figure out what is total number of electrons. Okay. So I'll start balancing right here, but I would advise you pause the video and try to balance it yourself. I minus is changing to I2. I have I minus right here, I2. I have 2I here, so it has to be twice. Next, I don't have any oxygen, don't have any hydrogen, so I'll move on to charge. How many charge here? 2 minus. How many charge on this side? 0, which means I need 2 electrons on this side. That balances this equation for me. Okay. Next, I move on to my second reaction, which is BrO3 minus changes to Br minus. Okay. What do? Balance everything but oxygen and hydrogen. 1 Br, 1 Br, so it's balanced. Next I move to oxygen, 3 oxygen, so I add 3 water. Next I need hydrogen, so how many hydrogen? 3 times 2, 6, which means I add 6 protons right here. Now I balance the charge. So what's the total charge here? 6 times plus 1 and 1 negative 1, which gives you a total of plus 5. Total charge on this side, I have 1 Br, which is negative 1, and 0 for water, so negative 1. So the lowest number is negative 1, so I need to come to negative 1. How do I do that? To come to negative 1, I will have to add more. I'll have to add 6 more electrons on this side, so it would be plus 6 electrons on the reactant side for this. So now if I have 6 electrons here, 2 electrons here, to balance out the total number of electrons, I'll have to multiply this reaction by 3, and that would give me a total number of 6 electrons for both of those, which means what is my N? N here is 6. So that's how I solve for N. Now I have N, I have E. I'll solve for Kc. If I plug in the value right here, E is 0.900 volt. Sorry, 0.90 volt is equal to 0.0592 volts divided by 6 log Kc. Right? So if you try to solve for this, you have to take entire log of everything. Solved right here for you. So to cancel this out, you multiply both the sides by 6 and divide both the sides by 0.0592. That would give you this right here, and then you take entire log of this, and that would give you K as 1.6 times 10 raised to power 91. Okay, moving on to next question. Lead can displace silver from solution, and silver occurs in trace amounts in some ores of lead. Pb plus 2 silver gives us Pb2 plus and 2 silver. As a consequence, silver is a valuable byproduct in industrial extraction of lead from its ore. Calculate K and delta G naught for this reaction. So again, no information is given to us for this question, which means this is coming from electrolysis. So that's how when you're doing questions in final exam, if no information about anything is given to you, no concentrations. If you want to solve for K, you know you need concentrations. No concentrations are given to us. If you're solving for G, you know you need either H, delta H values or delta S values, not given to you, or you need G naught F, G naught formation. That's not given to you, which means this question is from electrochemistry. Okay. So Now what do we need? We need K and we need G. Only information that we have is our chart. So again, you're going to go back to your chart, identify your reaction. PB is changing to PB2 plus, silver is changing to silver plus is changing to silver. So it's kind of getting very repetitive. So you go back, you look for these values, solve for E naught of the cell, and then you use the equations that are given to you to solve for K and G naught. Okay, so you can pause the video right here. Now you know the plan. Try to solve it by yourself and then come back and look for the answer. Okay. So if you look for the chart, you'll find these two values right there. Ag silver is 0.80, lead is underneath it, which means which one will be flipped? We will be flipping out lead. So if you flip the lead, your reaction would look like this. Silver would be as it is, lead would be flipped. To balance out the electrons, you have to multiply the top reaction by 2, which means your N in this case is 2. Okay, E naught, E for the cell would be reduction plus oxidation, so cathode plus anode, which would give you a value of 0.93. Then you're going to use this expression right here to solve for K. E naught is given to you, which is 0.93 equals 0.0592 volt over 2 is our N log K. You're solving for K from this equation right here. If you solve, your value of K comes out to be this. Now that I know K, I'm solving for G. What is the relationship that I know? I know delta G naught is equal to negative NF E naught cell, and I'm going to use this right here. So what is N? N is 2 moles of electrons. What is F? F is this right here. Whatever value will be given to you times E naught of the cell. E naught is given to us. We just calculated 0.93 volt. If you solve for it, it would give you a final answer of delta T. So that's how you solve for this question. Okay. Okay, so this is the last part of last type of questions you can get from electrochemistry, which is again related to equilibrium constant. So there is a relationship that essentially relates E naught of the cell or E of the cell with the concentration of our reactants and products, and that is given by Nernst equation. The derivation solved for you right here. Essentially, we are relating concentration meaning Q. Remember, this was a reaction question expression for a reaction. We are going to relate Q and E of a cell, and that's given by Nernst equation. How did we get to this equation? Let me very briefly explain to you. Of course, I don't expect you to know any of this, but this is just for your understanding. And finally, these two equations will be given to you in the exam. So we know that delta G equals delta G naught plus RT ln Q. We saw this in thermodynamics. We know delta G is minus NF E cell and delta G naught is minus NF E naught cell. If I put those two values, if I replace delta G with this, delta G naught with this, it gives me this expression. And now if I take NF common on both the sides and divide both the sides by NF, negative NF, that would end up giving you this reaction. So this divided by NF would cancel NF, this divided by NF would cancel NF, this divided by negative NF would give you this right here. So what you're left with is E is equal to E naught minus RT NF ln Q. And what we did here, we did the same exact thing at standard condition. R is 8.314, T is 298 Kelvin, F is 96.5 kilojoules per mole per volt, and that would give you this expression right here, which is Nernst equation. E cell equals E naught minus 0.50592 volt over N log Q. How can the question be formed? We can give you these two values and ask you the concentration, which is the value of Q, right? Or we'll give you we'll give you concentration of all the reactants and products, which will help you to determine Q, and E naught will be given to you. The question will be asking you for E cell. Okay, let's try a couple questions. Using the Nernst equation to calculate E cell, this is an example. In a test of new reference electrode, A chemist construct a Voltaic cell consisting of zinc to zinc 2 plus half cell and hydrogen to hydrogen plus half cell under the following condition. Zinc 2 plus is changing to 0.0. This is the concentration. Proton concentration is given to us and pressure in atmosphere is given to us. Calculate E of the cell at 298 Kelvin. Now remember, this is a relationship between concentrations and E of a cell. How can you relate concentration with E cell? It has to be done by Nernst equation. Concentration comes in the expression of Q and E cell is related to Q by Nernst equation. Again, the equation will be provided to you in the exam. Only thing you have to figure out how you can plug in these values. Okay, so there are two half cells. The question tells us there is zinc and zinc 2 plus. There's hydrogen and proton. So first thing, we have to go into our chart of reduction potential, find out which direction is the reaction going to happen. So if you go to your chart, you can from there figure out what is the E naught of the cell. So now if I go to my chart right here, you will solve for, you'll find the two reactions right here, and you'll see there that hydrogen reaction is 0 and zinc is negative 0.76. Based on that, I know that I'm going to flip the reaction of zinc. Okay, so we flip the reaction of zinc and that gives us this as the final reaction. So from here we know that E naught of the cell would be this plus this, that would be 0.76 volt. Once you have your E of the reaction, you can solve for Q. Now the question is asking for E cell, right? So what is the Nernst equation? Nernst equation is E cell equal E naught cell plus 0.0592 over N times log Q. I already have E naught, I have to solve for Q. So how do you solve for Q? Based on your reaction that we just saw, Q is going to be pressure of hydrogen times zinc 2 plus ion concentration divided by H plus concentration squared. Rest everything else will be neglected. Why? Because it is solid. Remember, solids are not included in this expression. When you plug in these values into the value of Q, you'll solve that Q comes out to be this. And then E cell would be E naught minus this log Q. We already know what is Q, we already know what is E naught of the cell. If you plug in the values and solve for it, your E cell will come out to be 0.86 volt. Right? I know this kind of gets very complicated till the end of it because this is all the information that you guys have studied up until now, meaning equilibrium plus Q plus values of E naught. So everything is combined together in this question right here, right? So it kind of gets very confusing. So you need to practice the questions like this. If you're not comfortable with calculating E naught of the cell, then it will become very difficult for you to come to questions like this. Okay, I can tell you one thing. I do want you guys to understand this concept and how we are getting here, but I will not be giving you any question in exam for Nernst equation. Okay, or if I do, it will be fairly simple. I will not expect you to figure out all these steps. Most of the times it will be very straightforward question, but I do want you to understand why and how everything is related to each other, how chemical equilibrium and Q and concentrations are related to E naught and E of the cell. Okay, the last part is all theory. There's a couple more sections given in your book. I do not want you guys to focus on that. Please ignore those sections. There's about fuel cells, different kind of batteries, how the batteries are charged and stuff. I do not want you guys to memorize any of that. Okay. Only thing I'm going to briefly discuss in the next slide or two is electrolytic cells. So I give you a brief idea of what the electrolytic cells are. Electrolytic cells are exactly opposite of a galvanic or a voltaic cell. Okay, so if you remember, galvanic cells are the ones that produce electricity, right? Electrolytic cells, on the other hand, are the ones that use electrical energy. Okay, galvanic cells are the one where spontaneous reactions are happening. Electrolytic cells are the ones where non-spontaneous reactions are happening. So meaning the reaction is non-spontaneous, that's why you have to supply electrical energy from outside for this reaction to occur. Okay, so you should know the difference between electrolytic cell and voltaic cell. That is, I can ask you a question of that. This is all theory. Okay, just remember galvanic cell is opposite of electrolytic cell. So if in galvanic cell we produce energy, electrolytic cell uses energy. Galvanic cell reaction is spontaneous, electrolytic cell reaction is non-spontaneous. Okay, we have to supply energy from outside. Non-spontaneous mean E naught for a galvanic electrolytic cell will always be a negative value because it's a non-spontaneous reaction. Okay, as with a voltaic cell, oxidation occurs at the anode, reduction occurs at the cathode. So this is the similarity between electrolytic and galvanic cell. Here also oxidation will occur at anode and reduction will occur at cathode. That does not change. Okay. But in this case, what is happening? An external source is supplying cathode with electrons, which is negative, and removes them from anode, which is positive. So here the charges of the anode and cathode have changed. Anode is now positive, cathode is now negative. Okay, so only similarity between a galvanic cell and electrolytic cell is what happens at the electrode. Okay, oxidation occurs at anode, reduction occurs at cathode. That is the only similarity. Rest everything else is opposite of a galvanic cell. Okay, galvanic cell produces energy, this uses energy. Galvanic cell is spontaneous reaction, this is non-spontaneous. In galvanic cell, anode is negative, here cathode is negatively charged. Okay, so why do we need electrolytic cell? This is essentially an example of when you're charging batteries. Galvanic cell is an example of when we're using batteries, right? So if I want like a toy which is charged by batteries, if I plug in that battery into the toy starts working. That is an example of a galvanic cell, right? It's happening by itself. Now, what is the opposite of that? That's an electrolytic cell. If you have a rechargeable battery and you uh, plug that to electrical energy. That electrical energy is the external energy which is going to do this non-spontaneous reaction. Okay, so that is kind of an example of a recharging of batteries. Okay, so this is showing you the example with difference between a voltaic cell and a electrolytic cell. So galvanic cell or voltaic cell, if you have these two reactions between tin and copper, based on the reduction potential, tin will be the one that will be losing electrons. So loss of electrons. So tin here should get oxidized and this should be your reduction reaction. Okay, and this would be a spontaneous reaction. But on an electrolytic cell, it's actually reversed. So this reaction would be reversed. Both these reactions are essentially reversed. Okay, so you can see right here the charges of the cathode anode are reversed. The reactions that are happening are reversed. So here the electrons are going from anode to cathode, and here also electrons are going from anode to cathode. What's also reversed here is that you can see here anode is written on left, cathode is written on right, like we have discussed before. But in case of electrolytic cell, it's reversed. Cathode electrode is essentially placed on the left, anode is placed on the right. Okay, so I'll not be asking too many questions about this, but essentially some brief questions like what is the charge of the electrode and where does a spontaneous reaction occur? So if you see electrolytic cell written in one of the questions or one of the options, you should know what an electrolytic cell is. All right, so that's majorly it. This brings me to the end of this topic, and that completes the chapter of electrolysis for you. If there's anything extra in your book, please ignore it. We will not be going through that topic, and that is kind of regarded as out of your syllabus context. Okay, so we'll just cover it, keep it until this topic.